I want you to imagine stepping out of a sterile, brightly lit, just really generic school hallway. And you push open this heavy oak door into a space that feels like it belongs in, well, another century.
Oh, or maybe a better version of our future, honestly.
Yeah, exactly. You are standing inside this solar punk Victorian naturalist field station.
Right.
It's a working greenhouse lab, and the air is slightly humid, smelling of, damp earth and growing things.
It's just beautifully atmospheric.
It totally is, and it's meticulously organized. You see these warm brass and glass details on the workbenches. There are field notebooks open on cream paper filled with this really intricate botanical line work.
And careful student hands, right?
Yeah.
Working quietly among the moss and the living systems.
Yes, but here is the fascinating paradox about all this. The 12-year-old brains operating inside this incredibly serene room are currently in a state of absolute cognitive chaos.
Complete chaos, yeah.
So welcome to the deep dive. Today we are unpacking a really fascinating stack of sources centered around a 7th grade life science resource page. It's titled Bioforge Educator Lab, 1.1.3 Planning and Carrying Out Investigations.
And it is a dense stack of material, too. I mean, we're synthesizing educational frameworks from the next generation science standards, neurocognitive research on the adolescent brain.
Which is wild, by the way.
Oh, totally wild.
Yeah.
And we're also looking at the highly specific design language of the Bioforge curriculum.
Right.
And that visual contrast you just set up,
Ah.
the calm environment versus the chaotic adolescent mind, that is exactly why this specific curriculum is designed the way it is.
Makes sense of that for me. How does the aesthetic tie into the science?
Well, the aesthetic is tied directly to this science and engineering practice, which we call SEP.
Okay.
In the Bioforge visual system, the primary color for this particular practice is a very specific moss green. It's hex code 5C7A43, actually.
Wow, they even have a hex code for it. I did notice that heavily in the source material. It is a very distinct vibe. There are absolutely no, neon stem graphics.
No floating cartoon beakers in space.
Right, none of that. It's entirely grounded.
Yeah, and that's intentional
Mm.
because Bioforge is actively pushing back against that chaotic, mad scientist energy that we usually associate with middle school labs.
Oh, I see.
Yeah, when you picture a science lab, popular culture basically tells you it should be kids mixing brightly colored liquids together until something blows up.
I mean, that was my middle school experience, so.
Exactly. But here, you look around and you see hand lenses, quadrant frames for ecological sampling.
Microscope slides.
Right, microscope slides, labeled jars. The entire mood is just careful, curious, and really disciplined.
Yeah.
This isn't about chaotic invention. It is about thoughtful, evidence-focused discovery.
Which perfectly brings us to the actual mission of this deep dive. We're looking at what it really takes to, quote, plan and carry out an investigation in middle school. And before we get to that neurocognitive chaos happening in these students' heads, we really have to define what an investigation actually is.
Because it's definitely not what most people think.
Right. Reading through this material, it is clearly not just handing out a worksheet and having kids blindly follow, step 1, step 2, step 3.
No, not at all. Following a predetermined recipe to get a known result, that is a confirmation activity.
Okay.
It's not an investigation. Planning and carrying out an investigation is the foundational practice that scientists and engineers use when they actually need evidence.
Evidence being the key word there.
Absolutely. The defining characteristic is that the students are the ones making the decisions.
So they're in the driver's seat.
Exactly.
Yeah.
They have to decide what question can actually be investigated, what specific tools are needed, how measurements will be recorded.
And what to do when it inevitably goes wrong.
Yes. Crucially, how to revise a plan when the first version completely falls apart.
I want to give you listening a metaphor to make this concrete, because reading through these Bioforge frameworks, an investigation really feels a lot like preparing for a field expedition.
That's a great way to look at it.
Yeah, you do not just wander into the forest shouting science and hope the moss explains itself to you.
I mean, you would be out there a very, very long time if you did.
Exactly. You have to prepare. You bring the right tools, maybe a hand lens or a quadrant frame.
Right.
You decide exactly what you were looking for before you even leave base camp. You record what you observe meticulously. And you have to stay intellectually honest about what your evidence can and cannot actually prove once you get back.
That's the systematic part of it. If we look at how this applies across disciplines, a good investigation is, at its core, a systematic process.
It doesn't just happen in the woods.
No, not at all. It can happen anywhere.
Hmm.
Traditional classrooms, greenhouses, field sites, schoolyards, or even simulated digital environments.
Yeah.
And if we look at the engineering side of this practice, investigations are specifically used to test whether a design works under different conditions.
Like stress testing.
Exactly.
Yeah.
You are systematically identifying failure points and constraints.
Well, wait, let me push back on this a bit.
Sure,
We are talking about 7th grade life science here. I remember being in middle school.
we all do.
The goal of a lab wasn't to systematically identify constraints. The goal was to get the perfect or right results so you could just get an A on the lab report.
Right.
I remember being absolutely terrified of getting the wrong data because I thought it literally meant I failed science.
And that fear is a massive misconception. It's something the modern science standards are actively trying to dismantle.
Really?
Yes, the goal of an investigation is never perfect results.
Never.
Never. The goal is reliable evidence.
Oh, that's a big distinction.
It is. The universe is messy. Living systems especially are messy. If your plant dies unexpectedly, or your data looks totally chaotic, but you collected it systematically and controlled your variables, that is excellent science.
That's so freeing to hear.
Right. Science is just the practice of finding reliable evidence within that messiness.
So if the universe is messy and the goal is reliable evidence, the only way to bridge that gap is through planning,
Exactly.
which sounds simple enough. But here is where the sources take a really fascinating turn into cognitive science. Because the act of planning an investigation absolutely crashes the adolescent brain.
It completely does. It creates a massive cognitive bottleneck.
Walk us through that. Why does it crash?
Well, when we analyze early adolescence, we're talking 11 to 14 years old, the prefrontal cortex is undergoing intense maturation.
Okay.
This is the region responsible for executive functioning and working memory.
Working memory being like the brain's temporary scratch pad, right? The RAM of the human mind.
Precisely. It's the system responsible for temporary storage and manipulation of information. And for a 7th grader, that RAM is extremely limited.
Like an old computer.
Yeah, they could only hold a few units of unchunked information at one time. Now, think about the sheer volume of parameters we are asking them to hold in their minds when they plan an investigation.
It's a lot.
It's a ton. They have to identify the independent variable they'll change, the dependent variable they'll measure.
Multiple control variables to keep constant, really.
Yes, exactly. Plus the tools they need, the safety requirements, the sources of error, and the number of trials needed to ensure reliability.
Okay, let me try to put this into perspective, because just hearing you list that is exhausting.
It's overwhelming.
It's like trying to juggle, but before you are even allowed to physically catch a ball, you have to mentally calculate its weight, its trajectory, and the wind speed.
Oh, that's a brilliant analogy.
Your brain literally drops the balls because there simply isn't enough processing RAM to handle the physical action and the mathematical planning simultaneously.
That is an excellent way to frame it. And when that RAM gets overloaded, the student doesn't just quietly sit down and ponder their next move.
What do?
They freeze up. Or, more often, they revert to highly intuitive, incorrect mental models. They lose the thread of the investigation entirely.
Wow. So if their brain's scratch pad is that limited, the jump from elementary school science to middle school science must be a total cognitive shock to the system.
It is a profound shift. I mean, in K through 5, students are mostly making guided observations.
The teacher sets it all up.
Right. The teacher builds the system, and the student just observes what happens. But by middle school, the training wheels come off.
They have to build it themselves.
Exactly. They are moving away from simple observations and are now expected to plan investigations with multiple interacting variables with a rigorous focus on evidence quality.
I want to ground this in reality for you listening. If you look around this Bioforge lab we imagined earlier, you see different teams of 7th graders tackling different living systems.
Yeah, all doing different things.
Over at one greenhouse bench, maybe a group is testing how light affects plant growth, utilizing elaborate plant growth setups and labeled jars.
Right.
And at another station, they're comparing single-celled organisms, carefully organizing their microscope slides and specimen trays.
Yep.
Another group might be observing variation in living organisms or designing a fair test for a model ecosystem in a terrarium.
Or investigating how resource availability affects populations.
Right, there are so many options, but instead of just listing these off, let's zoom in on one specific example to really understand this cognitive friction we are talking about.
Good idea.
Let's look at a team investigating how environmental conditions affect decomposer activity. They have, say, soil samples, roots, and decaying leaves.
Okay, this is a perfect example to isolate the pedagogical friction.
Walk us through it.
Let's say a 12-year-old student says, I want to see if a warmer environment makes things decompose faster.
Seems like a solid question.
It is. It's a great scientific question. They understand what a variable is in theory, but the moment they have to apply it to a complex living system, they hit a wall.
Why? What stops them?
Because they have to define what counts as data before they begin.
Oh, and I'd imagine clarifying what the data actually is the hardest part of that entire process.
It really is.
I mean, if I'm a 7th grader looking at soil decomposition, my intuitive thought is just, well, the dirt gets smaller, that's my data.
Right.
But I have no objective way to actually measure dirt getting smaller.
Yes. You've hit on the exact mechanism of the struggle. What is the actual data? Are you measuring the temperature of the soil with a thermometer?
Or measuring the mass of the decomposing matter on a digital scale over 2 weeks.
Exactly. Or are you using a quadrant grid to count the visible fungal colonies on the surface of the leaves?
There are so many ways to measure it.
There are. And if a student doesn't define the parameters of their evidence on their clipboard first, they will just end up staring at a pile of dirt 2 weeks later with absolutely nothing to write down.
Which has to be incredibly frustrating. I mean, they put in the time, but they have no evidence.
Yeah.
And because defining that data and controlling those variables is so conceptually heavy, the research shows students often stumble right at the starting line.
They absolutely do.
The sources actually outline a synthesis of common mistakes middle schoolers make, and they all seem to stem from this exact cognitive overload.
They do. And the most common pitfall, hands down, is cognitive impulsivity.
Okay, unpack cognitive impulsivity in this context. How does that physically manifest in the lab?
It manifests as the rush to act before thinking.
Ah.
When a student is overwhelmed by the demand to define variables, their brain looks for an escape hatch. And that escape hatch is physical action.
So they just start grabbing things.
Exactly. They rush to touch the flasks, the rulers, the measuring tapes, the hand lenses, the calipers, all before they even have a plan.
Because they think they need to be doing something.
Right. There is this deeply ingrained false assumption that doing equates to learning.
The idea that if my hands are busy mixing things, I must be doing science.
Yes, it's a false equivalence. They start playing with the quadrant frames or mixing soil samples, not out of malice or bad behavior, but because of cognitive overload.
But without a systematic plan, that impulsivity just leads to messy, unusable data.
Exactly.
And when they inevitably get that messy data, another major mistake kicks in. The sources call it hiding the outliers.
Oh, this is a big one. This goes back to that fear of getting the wrong answer you brought up earlier.
Right.
If a student is impulsively taking measurements and suddenly gets a weird data point, say, one soil sample is completely devoid of fungal growth while the rest are covered in it, their first instinct is to erase it.
They think they messed up.
Yeah. They think they did something wrong, so they try to hide the messy data.
Rather than treating that messy data point as a scientific phenomenon to be investigated in its own right.
Exactly. An anomaly is an invocation for more science, not a reason to use an eraser.
Okay, I have to play devil's advocate here again.
Go for it.
We are talking about 12 and 13-year-olds. Their prefrontal cortex is literally under construction.
Yep.
Aren't they just biologically impulsive? I mean, you can't just look at a middle schooler and say, hey, stop being impulsive.
No, you certainly can't. Telling a 12-year-old to just focus is functionally useless.
Right.
This is exactly why the Bioforge framework doesn't rely on just telling them to behave.
Right.
First, as we discussed, the solar punk aesthetic itself sets a subconscious tone of discipline.
It sets the mood.
Exactly.
Yeah.
But pedagogically, the curriculum uses a mechanism called just-in-time cognitive coaching.
Just-in-time cognitive coaching. That implies you are intervening at the exact moment the brain is about to drop all those juggling balls.
That is exactly what it is. Instead of teaching a separate, really boring lesson on how to focus on a Tuesday, and then doing the lab on a Thursday.
Which they'd forget anyway.
Completely. Instead of doing that, the curriculum embeds brief cognitive supports right at the friction points of the investigation.
Okay.
They integrate specific habits of mind directly into the scientific tasks.
Shifting the classroom culture from mere compliance, which is basically just following safety rules so you don't get in trouble, to actual scientific craftsmanship.
Craftsmanship is the perfect word for it. It implies care, intentionality, and a deep respect for the tools and the evidence.
And to help you listening actually build that craftsmanship, whether you're a student, a teacher, or just someone trying to troubleshoot why your internet router keeps dropping the signal at home, the sources detail a specific tool.
Yes.
We call it the Bioforge brain hack.
The Bioforge brain hack for the scientist habit of managing impulsivity.
And the core message of this hack is very simple. Slow down before touching tools or collecting data. Careful planning prevents messy evidence.
But the mechanism of why it works is where the real insight lies.
Right, because at first glance, the actionable step here just sounds like a standard middle school checklist.
Right.
The instruction is, before beginning an investigation, name 4 specific things. Number 1, what is the exact question being asked? Number 2, what is the one variable you will change? Number 3, what is the variable you will measure? And number 4, name one thing you will keep exactly the same.
Now, most science teachers have some version of that checklist.
Right, it's pretty standard.
But what makes this a brain hack in the Bioforge context isn't the list itself, it is the neurocognitive offloading.
Neurocognitive offloading. Break down that mechanism for us. How does writing down 4 things change how the brain works?
Think back to the RAM analogy. When a student approaches that greenhouse bench, their working memory is entirely consumed by the physical environment.
Right.
It's the smell of the soil, the presence of their peers, the shiny brass calipers, the glass flasks.
All that sensory input.
Exactly. If you ask them to also hold the independent and dependent variables in their head while they navigate that physical space, they will fail.
The juggling balls drop.
Yes. But by forcing the student to physically write those 4 specific things down on their moss green clipboard or in their cream paper field notebook, you are effectively offloading that information from their internal working memory to an external hard drive.
Oh, the clipboard becomes the external hard drive.
Exactly. You are freeing up their brain's limited scratch pad. They no longer have to expend cognitive energy remembering what they are measuring. The clipboard holds that information for them.
That is so smart.
It entirely changes their physical relationship with the lab tools. It forces them to translate their enthusiastic, impulsive excitement into a disciplined, systematic plan before their hands ever touch the specimen trays.
It is the physical act of writing it down that acts as the cognitive scaffold.
Exactly.
It's like writing down the complex recipe before you start chopping the onions. You don't have to hold the mathematics of the recipe in your head while holding a sharp knife. You just look at the paper.
And once that plan is secured on paper, they can actually execute the investigation with that true scientific craftsmanship. They can measure the roots with the calipers, observe the fungal colonies with the hand lens, and record their data systematically without getting lost in the overwhelming complexity of the living system they are studying.
This has been such an illuminating journey through these sources. I mean, we started by looking at the stark contrast between a serene solar punk field station and the sheer cognitive demand placed on the adolescent brain.
It's quite the contrast.
It really is. We realize that a 7th grader's working memory is pushed to its absolute limits, just trying to juggle variables and controls.
And we explored how that cognitive friction actually plays out when applied to living systems.
Right.
Moving past elementary K through 5 observations to really interrogate complex setups like how environmental conditions affect decomposer activity.
And we saw the very real danger of cognitive impulsivity, how the false assumption that busy hands equal learning leads to messy data and hiding outliers.
Which happens so often.
It does. And finally, we unpack the mechanism of neurocognitive offloading, how managing impulsivity through a simple embedded habit on a clipboard makes this high-level scientific practice possible.
It really grounds you in the world of the Bioforge Lab.
It totally does.
It paints a picture of a place where careful observation truly reigns supreme over chaotic mixing, where field notebooks are filled with systematic plans long before a single living specimen is ever touched.
The emphasis on intentionality is palpable. It honestly makes me want to grab a moss green clipboard, pick up a hand lens, and head straight into the greenhouse to see what I can measure.
Well, before we wrap up, I want to leave you with a final thought to mull over.
Okay.
We have spent this entire deep dive talking about tools, right? Flasks, quadrats, microscopes, rulers, calipers.
Those physical tools.
Right. But when you look at the cognitive research and you really understand the neurobiological demands of this scientific practice, what if the most vital scientific instrument in any laboratory isn't the microscope? What if it isn't the calipers or the quadrant frame or the digital scale? What if the single most powerful, essential tool in science is simply the trained discipline of the human mind, deliberately pausing to think before it acts.
In Bioforge, investigations are how curiosity becomes evidence.